Okay, so now we are going to solve this problem 14.8, this example from the book. And what is the story? We are at a reception. We have this 0.5 kilogram of ice, a chunk of ice, at this low temperature, minus 10 degrees. And we put it in 3 kilograms of iced tea. Iced tea, remember, is just water. So we put our chunk of ice into the water that is at 20 degrees. Okay? The question on the problem is, what is the temperature and in what phase will the final mixture be? So this is a problem that now involves two objects and has a phase change. Whenever we have this kind of problems, before doing anything, you should find out, you should estimate what the final phase will be. Because once we know the final phase, then we'll know which cues we have to add in this problem. Okay, so the final phase is the first thing that we have to do. In this problem, we know what the final phase is because we are very familiar with this kind of problem. Now, if we pick a glass of water and throw a piece of ice there, we know that the ice will melt and at the end we'll have everything is liquid, liquid water. Now, we know that when we put a chunk of ice into water, into Coke, we know that the ice just melts. But this is because we are familiar with. If we were playing with substances that we are not so familiar with, it's important to know how to first estimate the phases. Okay, so that's what we have to do first. Let's first estimate the phase. In other words, for this case, we already know it's the final phase is liquid, but let's justify why this final phase is liquid. After that, we can go for the equations and then obtain the second part of the problem, which is the temperature. Okay, so the first problem is the first point, the first item that we have to solve is phase. Okay, whenever we have problems involving phase change. Okay, so let's write down everything that we have. On the side of the ice, we have 0.5 kilogram. And the initial temperature of the ice is minus 10 degrees. On the side of the water, I see, remember, we're just going to be calling it water. We have 3 kilograms, and the initial temperature is 20 degrees. Okay? We also know what is the specific heat of ice. You can go back to the table, and that's 2100 joule per kilogram in Celsius. The specific heat for water using the international system is 4186 joule per kilogram in Celsius. There is phase change here, so we may also need the latent heat, the heat for fusion, and let me put also this information here. The heat for fusion is 333 10 to 3 joule per kilogram. Okay, this is all that we need for this problem. First thing, as we said, let's estimate the final phase. How do we do that? We have to find out how much energy we need to transform this ice into water, into liquid water. How much energy we have to inject to get this phase change. This is what we are going to do on the side of the ice. On the side of the water, what we have to do is estimate how much energy we need to extract for the water to become ice. Okay? We compare the two. The one that requires the least amount of energy, that's the one that will determine the final phase. Okay? So let's go. What is the energy that we have to inject to this 0.5 kilogram of ice for it to become water? Well, first we have to bring this ice, which is at minus 10 degrees, to 0. No? So the final temperature is 0. 0 minus 10 means the delta T here is plus 10. So this is the amount of energy that we inject just to bring the ice to the temperature of 0. So raising the temperature of the ice from minus 10 to 0. And then we need still more energy for this ice to break the bonds of this ice and for it to become liquid water. So here we'll have to multiply this mass by the heat of fusion, which is 333 multiplied by 10 to 3. Okay, so compute all that, no? Put all these numbers here, and you're going to get the final amount of energy that we need to transform 0.5 kilograms of ice into water. Okay, so how do we do that? This is 0.5, the C of the ice 2100 multiplied by 10, then 0.5 multiplied by 333, 10 to 3. This is a big number. I think it's something close to 170 kilojoules or something like that, for you to double check. Okay, it is a big number, and I think it's 170 or 177. Double check kilojoules. Okay. Now, how about the water? For the water to become ice, we'll need to extract energy. How much? Well, first we'll have to bring this water from its 20 Celsius to 0. So the final temperature is 0 minus 20. So here we have to multiply by minus 20. After that, the water is now at temperature 0. We have to keep extracting energy to create the bonds, so then the water will become ice. So we have to keep extracting energy from this water so it becomes ice. You put all these numbers there. No? So here 3 kilograms multiplied at 4186 minus 20, then minus 3 kilograms multiplied by 333,000, and we'll get a very big number. So I'll give you some time to try to do this in your calculator. Let's see what is the number that we get. I'm doing this now in my calculator, and I let you also do this in your own calculator. And then here you will see that we get minus, no, because we're extracting 1,250 kilojoules. Okay, and on the other side, I said it's 170. Let's double check. Go and do it in your calculator, and I'm also doing it here in my own calculator. What is the amount of energy that we have to inject in the ice for it to become liquid? Well, it's not 170. Now I double checked. My calculator is 177. Okay, but that's the important point, is what I said. Now I can compare the left and the right. Okay, for the ice to become water, no, for that little chunk of ice, 0.5 kilogram, to become water, I need to inject this much energy. Now, for the 3 kilogram of iced tea, this 3 kilogram of water, for it to become ice, I have to extract this much energy, which is much more than what the poor ice can give it. Okay, well, this amount is much more than what the little chunk of ice can extract from it. Okay, so for sure, the 3 kilogram of water, of tea, will not become ice. What is going to happen is the little chunk of ice will be stealing energy from the water, and the water will be giving, the tea will be giving energy for the ice, and the ice will melt. So that's what I said in the beginning. We do this analysis for the two objects involved. The one that requires the least energy, which is the ice in our case, the one that requires the least energy is the one that will determine the final phase. The ice will become water, okay? Because the water has enough energy to give to it, okay? So the tea has enough energy to give to the ice. So the ice will become water. The final phase of this system will be liquid. All right? It is sort of trivial in this problem. We already knew, we already expected, but now you know the justification. And do this analysis before, whenever you have phase changes involved in the problem. Okay? So the object that requires the least amount of energy to change its phase is the one that will change the phase, is the one that will determine the final phase. Okay? All right, so given that, we can now go for the second part of the problem, which is to find this final temperature. So how do we go? To find the final temperature, we are going to sum all the Q's involved in the process. The sum of all the Q's will give us 0. So let's see what is going to happen to that chunk of ice. First thing, the chunk of ice will go from its minus 10 degrees to 0. Then this chunk of ice will go from ice to liquid, to water. Okay, so first we inject energy, so the chunk of ice raises its temperature from minus 10 to 0. Once we are at 0, the chunk of ice will keep stealing, will keep getting energy from the tea, and it will then melt, will become liquid. And once it became liquid, it can still raise its temperature a little more. Now from 0 to a certain final temperature, which we don't know, which is what we are trying to obtain. All this is what is going to happen to our chunk. Oops. I wrote it wrong here. To our chunk of ice. But we also have the Q from the water. What is happening to the water? The water is just dropping its temperature a little bit because it's giving away energy for the chunk of ice. Okay, so for the water, all that we have is it's initially at 20 degrees. It's going to drop its temperature to a final temperature, which is the one that we are trying to obtain, and that's it. Now it will be losing energy. This is what we have for the tea, for the iced tea, which is water. So it's going to drop its temperature a little bit. It will give away energy for the chunk of ice. So the sum of all this is equal to 0. From that, we can now get the final temperature. Okay, so how are we going to do that? Let's put the term for the chunk of ice. Remember, the mass for the chunk of ice is 0.5. Here we put the C for the ice, 2100. Remember that I wrote it here, the C for the ice. So this is what you have to put here. And then changing temperature. The final is 0. The initial is minus 10. So 0 minus 10 will give us plus 10. Okay, so what I wrote here, 0 minus 10, that's why I get plus. Okay, continue with the chunk of ice, 0.5, and now we are going to change phases. So we just use ml, right? When we are changing phase, there is no changing temperature, ml. What is L? 333, 10 to 3. Okay, so this is for this piece. ice now, this chunk of ice, this 0.5 kilograms that was ice, now became all water. So now we have here 0.5 of an ice that is now water. So careful now with the C that you're going to enter here, because this specific heat is now the specific heat for liquid. Okay, our ice now became liquid. And, well, the changing temperature, I'm going to put here the final temperature, which we don't know, minus 0. Well, the 0 is unnecessary, but this is just to indicate is the delta T. So I wrote everything that is happening to the chunk of ice. Let's add to this story the T, the 3 kilogram of T. So we have 3 kilogram of T, C of T. So this is C of water. This is the T. And final temperature, which we are trying to obtain, delta T here. So final temperature, TF minus the initial. What is the initial temperature of water? 20. All this equal to 0. That's the equation that we have to solve to get the final temperature. But be very careful with these specific heats. Here, the ice was still ice, so here you're going to put 2100. Here, the ice became water, and here you're going to put 4186. Okay? And on the side of the water, on the side of the T, well, it's liquid, so here you put 4186. Now you have all the ingredients to find that final temperature, and you will see that the final temperature is 5 degrees.